So anyway, I appreciate the intro. My name is Dr. K. I'm the CTO of Dominant Strategies and the co-founder of Quai Network. So before I dive into PoEM, or Proof of Entropy Minima, I'll just start with context of why are we interested in new consensus. And basically the premise for Quai Network is that if we want to actually get crypto and cryptocurrencies ubiquitously adopted, we have to service a lot more people than it currently can service, right? So in DeFi, people kind of focus on a niche and they say, oh, we're going to get to the next billion users by expanding DeFi, but there's only 700 million TradFi users, so saying that you're going to get to a billion DeFi users is somewhat apocryphal. So our premise is if we want to get to a billion users using cryptocurrencies, we first need to function as money. To be able to function as money, we need a technical scaling requirement. And so if we look at cash and electronic payments, we can come up with an estimation that 50,000 TPS for the world that has the infrastructure access to use cryptocurrencies is about the sort of the target that we're going for. And then the way that we're going about doing that at Quai Network is that we're using a hierarchical network of merge-mined blockchains. This allows us to dynamically increase throughput by maintaining the security of sort of a proof-of-work system. So if you look at here on the left, we have a first-generation blockchain, which is just like a simple sequence of blocks. And if you look at Quai Network, it's this hierarchy of many blockchains that are progressing asynchronously with time. And I'm going to dive into that a little bit more, but basically the idea here is if you want to think about this in another way, the sort of zone chains there are the ones sort of updating state and processing transactions, and the region and prime chains are these coordinating layers. And we'll talk a little bit later about how PoEM sort of applies to that coordination mechanism. So the question though is, how do we get to that 50,000 TPS? And there's a number of ways that we can do it. And we need a couple of these things put together to actually go from 5 TPS to 50,000 TPS. So one way that you can get there is obviously shards. Sharding in a proof-of-work system obviously presents challenges. Specifically, how do we shard state without sharding work? And how do we create objective inter-shard referencing between the shards? Subnets also can get us about a 10x increase in throughput. The way we do that it does that is by decreasing bandwidth, decreasing compute. And when I talk about subnets here, I'm not talking about subnets from sort of like an avalanche perspective. I'm talking about it from a network topological optimization perspective. So when we talk about how performant is a set of nodes with communicating data, right? We want to minimize sort of the number of hops in the network. We want to minimize the latency between the nodes, their ping times effectively. So that's effectively what we're talking about with subnets, and we'll go into that a little bit more as well. One of the challenges, though, is then how do we incentivize optimal subnets, especially in an open permissionless system? And then how do we also prevent partitioning attacks once we've introduced subnets? The last thing we can do is streaming, which will allow us to decrease bandwidth and decrease compute. And when I say streaming, I mean streaming of computation of blocks. So when we think about the performance of a node in a blockchain, it's a very bursty performance where every sort of epoch or block that comes in, we sort of instantaneously recompute state. If I'm able to do something where I can start to understand what the block is before the block being found, I can speculatively execute on that and then resolve my differences later, so I can sort of stream computations. So between these sort of three things, we can get to sort of our 4 orders of magnitude that we're shooting for. The question is, how do we do it? So the first 2 are basically, we need PoEM to do them. And then the streaming one, we need PoEM plus something called a mine transaction. And so with that like context, we'll talk about PoEM now and sort of what PoEM is. But to understand PoEM, let's just first zoom out a little bit, talk about contention. So what is contention in a proof-of-work system? Very simply, if I have 2 blocks and I'm extending the chain, I may have a situation where, because of the fact that I'm in a distributed setting, 2 people find blocks before they know somebody else found a block, right? So somebody in Europe finds a block and they start broadcasting it to the network, but during that transmission time of propagation, somebody in the US also finds a block. It starts propagating through the network. So now in the network, we have 2 blocks, and in proof of work, they have the exact same preference or total difficulty. And depending on the order in which you receive those two blocks, you'll have a certain preference. So whatever block you receive first, you'll say, that's my block that I'm going to work on. And so obviously the problem is the people in Europe will have received, say, A first, whereas the people in the US would have received B first. So we now have a network that's in contention. Half the network's working on A, half the network's working on B. So this fork is due to the network delay. And then what ends up happening is we don't actually resolve this contention for one more block. So in Bitcoin, that takes time, and that time's about 10 minutes because that's our expectation time for a block. So this mining creates a block with equal weights, but because those blocks are equally weighted, that is what creates contention in the network. So the question is there a solution that will allow us to resolve fork faster by removing the contention in the preference of a forked block? So in current PoW, the blocks are assigned the threshold weight. So we have a threshold, and then when we find that block, if our difficulty is 100,000, that block is assigned 100,000 weight. It doesn't matter sort of what the hash value is, as long as the hash value is less than that threshold value, it just gets that. So let's introduce the idea of intrinsic proof of work. So with intrinsic proof of work, instead of just counting these leading zeros, or sorry, just the threshold value, what if we started counting sort of all of the leading zeros and even potentially the fractional zeros, so to speak, after the leading one? So effectively, what if we were thinking about the logarithm of the hash value? If we do this, the interesting thing is that the blocks are never equal. So in the same case where I have a fork that has a common parent, instead of necessarily having the same total difficulty, they will necessarily have different total difficulties, right? Because if I'm taking the log of a hash, assuming certain degrees of precision, I'm guaranteed that those two things will not have the same, they will never collide, right? The same guarantee of not having a colliding hash is the same guarantee that I won't have colliding difficulties. So if we do that, that's really cool. So in the same example, if I'm taking sort of the chain, this intrinsic PoW, we can see in the same example, one of the blocks will always be preferenced. So we'll still have that generation of an orphan block due to the network delay. However, the cool part here is we've gotten rid of the time to resolution of that fork. So the second that both blocks have fully propagated through the network and everybody is now consistent on the data sets that they've seen, everybody will make the same choice. Regardless of order in which they've received the blocks, they'll be working on the same tip. So beautiful. So measuring intrinsic weights provides an instantaneous preference. However, there's a problem.
Sorry, could you say again, why is the probability that the number of leading zeros isn't the same? Why is that negligible, or like what's the chances that?
Well, in the simple form, you can think about it as leading zeros, but obviously if I'm only looking at leading zeros, there's sort of a Bernoulli trial that's taking place by the number of extra zeros I've found past the threshold, which means I would have sort of a collidable preference. But if I think about everything after the leading zeros as sort of fractional zeros, which I would do by taking the log of the hash, if I do that with the same precision as the hash itself, right, I could have 21.2648325 sort of zeros, so to speak. So that's how sort of you carry forth like a preference, but the preference is as uncollidable as the original hash. Yep. So, the intrinsic weight provides that instantaneous preference. However, it does create a problem. And that is that it creates a withholding attack. So if we're looking at sort of how we're measuring that, if we do an example where someone gets lucky, and when we say lucky here, it's not even lucky, it's just given enough samples, an attacker will get something that has many, many extra leading zeros over the threshold just by the total number of queries or successes they've had. So if an attacker has, I guess what, they've found 1 million blocks, 1 in 1 million of those will have effectively 10 bits extra sort of zeros in front of the number. Right, and what that allows them to do in this simplified proof of intrinsic work setup is it allows them to hold the block for a very, very, very long time. So in that same example, if I'm doing like total difficulties here, and this total difficulty was one of these lucky blocks, so to speak, the honest chain is in the bottom here, the honest chain is progressing, the attacker just doesn't show their like very lucky block, and they can hold that back from the network for, in this case, 10,000 mean block expectation times. And then they can reveal it, and at the point that they reveal it, that will have a higher preference in the network, and things will get reorged back. So measuring intrinsic weight by itself makes it so that we don't have collidable preference, but it removes any finite finalization guarantees in the blockchain. So then the question is, well, what can we do to fix that? So what we need to do is change to use intrinsics, or sorry, what do we need to change to this concept of intrinsic POW to maintain a finite finalization time? And what we really have to ask ourselves is, what is POW? And like, what is difficulty? And when we think about it, it's actually a physically meaningless quantity, right? And the reason it's physically meaningless is because it is thinking of the weight as a series of independent events. But blocks are not independent events. Blocks are dependent events. The achievement of the hash threshold on a randomized oracle's query is an independent event. However, the fact that the subsequent block has a hash pointing back to the previous block makes the block itself a dependent event of the previous block. Does everyone see that? So the problem is when we talk about POW, it's adding up the preferences as if everything was an independent sequence, which is obviously not right. So the question is, can we design something to not do that? And the idea here is that we can use entropy. And if we want to think about this from an information science standpoint, if we think about a blockchain and we think about every time that I have the ability to sort of create a new hash, before I do any hashing, what is the opportunity in my field? The field size is 2 to the k, right? So I have 2 to the k sort of paths I can follow. Now, if I get a hash, and that hash, has so many leading zeros, what did I just do? I just shrank my field dramatically by however much sort of I've taken out of the field, right? So if you think about this from an entropy concept, every time we're finding a block, what we're doing is we're reducing the number of paths that we can take in the progression of the chain, right? So if I find something with, that 10 bits of entropy again, I've removed so let's say it's 10 bits of entropy. So if we have sort of 2 to the 256 as our field size, and we've removed 10 bits, that's 2 to the 246. If you think about that, I've removed 99.999999% of my field, every time I do a threshold hash. Now, any hash that wants to compete with that then needs to fit within the remaining option size to further reduce the entropy and keep going. So anyway, the idea here is, instead of having this physically meaningless quantity, let's think about this as an entropic progression, and let's measure the entropy of each step, and then weight based off the total entropic progression of the entire chain. So the way that we do that is we measure the reduction in the number of paths. And the way that that's done is this equation here, which is just n, which is our field size, n, the amount of sort of bits that we've removed out of the system, is equal to L, our field size, minus the log of the hash. And then what we can do from there is we can treat this as a series of dependent events, because we know that's what that is now, and we can multiply our bit reductions with each block. So if I'm multiplying in a linear field, that's the same as adding bits in a logarithmic field. So now we have a system where if I were to withhold that block, in this example, sort of our bits here is 36 bits. So that's 36 extra bits for that block. That was our 1 in a million block that the previous attack could withhold for 10,000 blocks. In this particular attack, this attacker can only withhold that for 2 blocks. Right? And the reason it can only withhold it for 2 blocks is because we're now measuring sort of the total mathematical combinatoric process correctly by treating the blocks as a series of dependent events. Right? So computing entropy with intrinsic weight removes contention while still maintaining our finite finalization guarantee. Any quick questions on that? No? Good? So when we think about this, we've been thinking about this for a while. We've used it obviously in a real system. but we kind of want to get sort of a better understanding of what we're actually trying to do here. So with mathematics, which is kind of what I've been, I guess, harping on, is that we're just measuring sort of the idea of the real possibility of having a sequence of dependent events. So I can think about this as a sort of a proper combinatoric treatment of the system. From a physics standpoint, what we're trying to do in a proof of work system is we're trying to make the system expensive to reproduce, because that is how we make the system sort of immutable and finalized. So from a physics perspective, we can think of a reduction in entropy as expensive, and if we measure the entropic reduction accurately, that will allow us to choose the most expensive outcome, which is the best outcome when trying to cooperate to make an immutable system. From an engineering standpoint, there's also an interesting sort of interpretation. If we think about hashing as a physical process, and as an engineer, what we're trying to do is sample that hash rate accurately, it's impossible to measure perfectly because we can't measure every single hash in the system. If we wanted to know the hash rate of the system, what we would do is we'd say everybody that does one hash, provably report that one hash to us. We'll aggregate this in a system, and we'll have a perfect measurement of the system, right? But the problem is, we obviously can't do that because there's petahashes a second. So like given time constraints and bandwidth constraints, we can't measure every single hash in the system. So what we do is we take subsamples. And the way that we're taking the subsamples is by using the thresholds as a sampling mechanism. But the problem in doing that is every time I take a sample, that sample has variance, right? Like engineering. If I take one sample by itself, like that sample will have variance within the size of my possibilities. And like that is the problem with proof of work. Right? So what we need to do is if we decrease the number of samples, we know the sample variance goes up. So when we do the treatment of that in our set, we have to discount it by the amount of variance in that sample. And the interesting thing is that that's effectively what PoEM is doing without us even having to compute the variance. So there's three different ways to sort of think about this. But the cool part about this concept is entropy is a time invariant mechanism to allow us to choose heads and coordinate chains. So if we go back to our original example of A and B, the cool part is if he gets A first or he gets B first, he's gonna have the same preference as me. So the order of arrival, that timing of arrival for everybody in the network is now inconsequential, right? So there's also another way to think about that. As that propagates out in the network, we always will make the same decision without us having to talk. So like normally in Bitcoin, to kind of know that we're there, we have to go back and forth. Because if I have a block, and I send it out, and then he gets it, he doesn't know that I agree with him until the next block. So there's this 2 rounds of communication that are taking place, right? But in this system, once that block propagates out, we all know that we're in consensus. So the really interesting phenomenon of this is consensus is no longer like this active ongoing act. It's, did we start the same code base with the same genesis block? And from that point forth, we always know we will be in consensus. Now, some people will say, but what about the data? And that's a very fair point. But when we think about what we're doing in a blockchain system, we have to think about consistency, independence of consensus, right? We need to separate those two ideas in our mind. Now, if I know that I can always hit consensus, now I just have to worry about consistency. So I can't infinitely sort of scale this thing. I'm still bounded by the propagation of data, but only by the propagation of data, and only by the propagation of data in one direction. I don't have to do rounds. And the problem is the second that I do a round back and forth, I don't know if I'm gonna have to go back and forth again, right? So like when I have that sort of non-finite time, I don't know how many times I'm gonna ping back and forth until we hit convergence. So the really cool part about PoEM is because it's only this outward propagating process, I don't have any sort of limitation of how many times I have to go back and forth before we all agree, which is pretty cool. So the difference between PoW and PoEM is even greater though when we start talking about like dominant chains and subordinate chains is how we call them. So if you recall the conversation of sort of how the hierarchy is formed in Quai Network, we have prime, regions, and zones. So, prime is sort of the biggest chain and it runs at the slowest rate. Regions are below primes. They run at a slightly faster rate, and zones run at the fastest rate, and they're the ones that carry state. So we can kind of think about region and zone as the coordinating layers. And this introduces this concept of a coincident block. And a coincident block is basically when we meet a threshold which is valid in more than one context, right? So if I meet a threshold that's very low, I'll find a zone block. If I meet sort of the threshold requirement for a region block, I'll find a region block and a zone block. And then if I meet the prime requirement, I'll find a zone, region, and prime block. But that block will have the same hash in all three contexts. Because what we're doing is we're merge mining the header. So we create a header that we think may be valid in all three contexts, and we search for single nonce to create that block in all three contexts. And then when we find that, we get what we call this interlink block. I'm referring to it here as sort of a dominant block and a subordinate block, right? So the question becomes, with this sort of hierarchical concept with coincident blocks, how does PoEM influence the finalization time in a dominant subordinate setting? And so if we look at POW, our finalization sort of guarantee for K is greater than 2 to the MD, where MD is sort of our dominant threshold. So if I'm sort of 5 bits above for a region block, that means that 1 out of 32 blocks would be a region block. However, the problem is if I use a strict POW treatment, it means that every region block can be withheld for the mean expectation time of a region block, which is 32 zone blocks. So effectively in this dominant subordinate setting, I never get a finalization guarantee of any of my dominant blocks because someone could always withhold every dominant share for effectively the mean expectation of the dominant time. So you can basically not create a hierarchy using POW. And that's like why we have sort of thought about this and come up with PoEM, is now with PoEM, if we do the same treatment where MD is the 5 extra bits and MT is our lower threshold bound, in this sort of 256-bit field, we can always guarantee that K will fall between 2 and 10 blocks, right? So because it's between 2 and 10 blocks, like we now have a reasonable system, and if we pick like a good MT value, our lower threshold value, we can really make sure that that K is, in all cases, 2 or 3 blocks. So now we can get sort of a finalization guarantee even though we're using this dominant and subordinate chain relationship. So what that means is that PoEM is solving the withholding problem because it's able to fairly weight blocks, not just in a single chain context, but in a multi-chain context, as well as a context with both dominant and subordinate shares. And one of the interesting outcomes of this is that there's such a thing as an optimal hash function. So if people sort of have been around in crypto a while, there was like this time period in, I don't know, maybe like 2012 to 2014, where people were like making a bunch of forks with a bunch of different hash functions, and they'd make sort of economic rationalization arguments about CPUs being centralized or GPUs being decentralized or like ASICs being centralized. And they would always talk about sort of the economics of the hardware used to do the mining. But no one ever sort of talked about the efficiency, right? So Bitcoin picked SHA-256, which can be very sort of performant, certainly in an ASIC setting. But people are like, that's not fair. We want more people to have it, so we'll move to Scrypt because we think Scrypt is GPU friendly. But Scrypt is way more inefficient in generating hashes per electron than SHA. But in the proof of work setting, we don't care. Like we really, literally do not care. However, with PoEM, we actually care about one hash function over the other hash function because it influences that MT value, and that MT value influences our finalization time. So what this means with PoEM, it actually gives us this, this weighting function to compare hashes, which is crazy because like no one's ever sort of been able to say how does my hash function influence my consensus and finalization, but like PoEM says, you would like to have the hash function that maintains collision resistant one-way property, right? And it has, a homogeneous outcome over the field size, but we would like the smallest field size with the most efficient algorithm so we can maximize that denominator and have the fastest finalization. So like crazy sort of outcome. So PoEM provides an objective mechanism for choosing the hash function. And that's why I was saying when we talk about K, if we can get a good denominator, we can kind of get a good function. So if I can get that to 60 bits in a 256-bit field, the absolute worst case for a withhold would be finding like the nil hash, which is 256 bits over 60, which means you still could only withhold the nil hash for 4 blocks. Crazy. And that's the nil hash. Like that'll happen once in the heat death of the universe. So like in sort of real expectation, like nothing ever is going to be withholdable for more than 2 or 3 blocks. So that's pretty cool. So diving deeper into sort of the multi-chain application in Quai. So we've talked about how we remove contention. And the reason that that is so important is because as we have more shards, our contention becomes exponentially more expensive. So if I have one chain, right, and I'm trying to decide things in one chain versus now trying to decide things in 2 chains, our coordination cost here just doubled for both of us, right? And then if I go to 4 chains, it's going to double again. So every time I add a new context, I'm exponentially increasing my coordination cost. So if my coordination cost isn't 0 in one context, like very quickly, it becomes untenable if I have many contexts. So the way this works in a multi-chain context is our coincident blocks create a multi-context commitment. And that's how we create objective referencing between the different shards. So when we have the different zone chains, right, they're asynchronously progressing. And then when we get these cool coincident blocks, it allows that zone chain to see everything else that it can reference back to in the hierarchy. So as it keeps progressing, you can see on a delayed sort of global basis in consistency, we eventually can reference everything else. So the way that we're actually doing the scaling trick is we're saying we're going to do this coordination as efficiently as we possibly can in a single chain, but we're going to take the penalty of having time to global finalization, right? So if I do a transaction in a single context, it's like sort of Ethereum sort of guarantees. You get an inclusion in 10 seconds, you know, n blocks of depth, you can call that finalized, you're good to go. Then you get this idea of these external transactions or these cross-context transactions. Those are dependent on the time that it takes for the hierarchy to reference the other things via coincident blocks. So the bigger the hierarchy becomes, the longer it takes to be able to actually finalize a cross-context reference in the destination and be able to respend it. So like that sort of is the magic that we're like, that's our compromise, right? If I tell you I can scale something infinitely, nobody else can scale it, and I don't tell you how I'm doing it or what I'm giving up, like I'm lying through a mission. So the real deal here is as the hierarchy scales, the time to global settlement logarithmically scales with the number of shards, right? So, you know, we can practically do something at, say, 100 shards. It will take a day to do, like, global settlement, right? So, so we've kind of gone over how in the dominant and subordinates we can create shares. When we're weighting the system in this context, basically all of our dominant blocks are inheriting the entropy of the subordinate shares. And then effectively what we're doing to compute the weighting is basically when we find a new reference, we add up all the things that are referencing back that we haven't added in yet. So maybe an easy way to think about that is if I'm here and then I find this next coincident block, every block that just turned red, I get to add in to that tip entropic weight because it just made a reference commitment to those references. So basically every tip is eventually adding up all entropy in the system. And then what that does is it makes it so that all the tips have comparable entropies. And it also gives a strong incentive to coordinate. Because if I'm just on a chain and I don't have an incentive to reference the other chains or reference the dominant blocks, I'm not going to do it. So because I add those things in, every time they get added in, they make my weight of my tip much, much stronger when I do it. So I have a very strong incentive to mine valid, cooperative, referenced dominant shares. So just a quick summary on PoEM then. We think that PoEM is the way to create hash-based blockchains if it's in a single context or if it's in a multi-chain context. The reason for that is that it creates a time invariant sequence of events. Like, so this is sort of really the interesting meta, right? Is that it's time invariant. When we look at our analysis using PoEM, we do not have a T. The only reason that we think about T at all is because we're trying to fit it into something like the back mode model, the synchronous model, or the partially synchronous model. But from our perspective, it's not a good representation. We don't need to think in rounds. We don't need to think in epochs. We just need to think in sequence progression. So there's no T in PoEM. There's no T in the measurement, right? So it like very much is a time invariant process, right? Because it doesn't matter what order the blocks arrive in, and the comparison, so that's the really cool part. The comparison of design choices here becomes trivial because we don't have T in the system. Every question we have seems to have a closed form solution. So if you say, how many chains should I have? Or how filled should my blocks be? Or whatever it is, because there's no T in the system, we can usually create an integral to approximate the system, because in a 256-bit field, this technically isn't continuous, but we'll make that approximation. So all of our questions have closed form solutions, which is like crazy if you've done security proofs on blockchains. The other thing that's cool here is any divergence is resolved instantaneously. So we don't waste time in hash to determine the best head choice. This also allows fair comparison between blocks or any sequence of blocks. So if you think about the question of, well, why don't I just do sort of a lexicographical choice on a Bitcoin block to determine A versus B? That's only true for one block. With PoEM, we're saying we're doing a lexicographical choice that's compounding with every sequence. So every choice is the representation of everything that's come before it, not just the previous block. And that's sort of a really important concept to get here as well. And then the cool part with that is that we can coordinate an arbitrarily large number of chains, and we're only limited by our data propagation times and our global transfers. And then I'll just say, in some ways, we kind of just like found this thing. We didn't really sort of invent this mechanism. We just were observing and doing experiments, and we like sort of found this. And we're like, sweet, this is shiny. What can we do with it? Because we were kind of trying to solve this question of how to do this hierarchy of chains. So I'll stop there super briefly. If we have any questions on like the PoEM piece, and then I can quickly just cover subnets. And I think I'm just doing shards and subnets. I don't have streaming in here, but cool. So the next piece that we can kind of go over, this is probably actually a little bit easier, but is how do we do sharding with PoEM? So this is the idea of merge mining. So when any producer in the network is sort of trying to produce a block, they're going to propose a header, but the header is going to have information for all three contexts, right? And then depending on the threshold they get, they'll find one or more blocks. So if I find the zone threshold, I'll have a zone block, and the rest of this data is effectively superfluous. If I find a region threshold, I'll find a region and zone block. And if I find a prime threshold, I'll find all three. And then again, the cool part about that is when this happens, I have a block in the block chains that has a single hash. So there's an objective hash linked reference from one chain to another so that every one of these state updates can be traced back and objectively proved from its origin with, you know, sort of a NEPO POW on top. And that's sort of how that cross-chain, quote-unquote, coordination is taking place. So then the cool part about sort of this merge mining process is that eventually every shard is committing to the global state, and every mined shard is also contributing to sort of the work in prime. So what happens here is like these individual sort of asynchronous chains are progressing, but eventually they're all referencing prime. So everybody's contributing to the weight of prime. So the total finalization of the system like is everybody. It's not just like I've sharded the thing and this is 1/10 of the system security. Eventually it all is 100% of the system security. And the reason that we have regions is to kind of give an incremental step. So like you need a region to sort of get better security guarantees as you're going up. Because if I had like a 2-layer, like very flat architecture, I could say I have 100 shards, but like this only has 1% of the hash. So the time that I'm sort of getting the cross commitment is like way longer. So by having regions, it's sort of guaranteeing that every time I go to the next dominant reference, I have to have that much hash to be able to execute an attack on the system. So if I'm in, say, a 9-shard topology, each shard is independently having, say, 11% of the hash rate. But the second that I get to the expectation value of a region block, to keep an attack going, I would have to have half of the region. So instead of going from like 1% to 100, right, I'm going from this like 11% to 33% to 100%. So that makes it so that your sort of guarantees in the subordinates are timely, so to speak. So the other thing that this allows us to do is it allows us to organize the Merkle root in a very structured way. So the way we sort of separate out this tree is by address space. So we shard the address space. So basically, this shard, if it's 0, sort of it's in shard 0. If the first bit or byte is 1, it's in shard 1, so on and so forth. So the first 2 bytes kind of determines what address has validity to be operated on in which chain. The other thing that's really cool about that, though, is if you make an addressed ordered tree, it also means that it's like really, really easy to trim. And the other thing that's cool about that is when I trim it and I do these sort of external referencing, I only have to send the portion of the tree to the destination that it needs to know about. So because we have sort of this like meta of a tree of chains, and we reflect that meta in the state root organization, it's very simple and concise to only trim the state that needs to go to the destination. So we can kind of create these very concise partial blocks and forward propagate them in the network, which is also a cool feature here. So when we do a transaction, right, that transaction sort of finalizing in a zone, we know that that block may end up being valid in its destination, but we don't know if that's going to be canonically referenced yet. But what we can do is we can forward propagate that portion of the block to its destination. And then when we find like a region reference or a prime reference that says, yes, indeed, that thing here has been canonicalized at the destination, all I have to do is check that it's in the Merkle. Like I already have the data at the destination. I've already validated the data. I can validate like all the signatures and transactions. I just need the manifest of what is my valid prior references. So you can forward propagate all of your data from your origin chain to your destination chain prior to it becoming canonicalized, which then makes that sort of cross-chain update very efficient. So in our system, we've actually made the decision to, right, because if we're sharding the address space, there's sort of a difficulty with ontological expansions or contractions. So what we've done is we've just said, there will be up to 16 regions, and there will be up to 16 zones in every region, so we can have a total of 256 total shards, and those are assigned at the beginning. So, when you're in a one shard topology, 255 bytes of the space, I guess, however you want to call it, is not valid, and every address has to start with that like 0 byte. And then as you expand, more and more of the address space effectively becomes valid. So we've gone over coincident blocks, and that's how we do our objective referencing between chains. And this is like a cool sort of graphic to kind of think about how like a transaction is moving. So we have an example here where we're sending in the bottom left there Cypress 1 to Cypress 2. So let's just sort of think about that starting as an epoch in time. We don't like to talk about time, but let's for this illustration, just think about that as all being at the same time. So then what happens is, and then we're also going to send a transaction from Paxos 2 to Cypress 2. So we have in the bottom here what we'd call like a close coordinate transaction. And in the top, we have like a far coordinate. So what would end up happening is as we start mining blocks and progressing, our Cypress 2 has now found a region block. That region block has a hash linked reference back to the originating, TX1 and Cypress 1. So now Cypress 2 can sort of finalize that transaction and re-reference it as it goes forward, right? So that can happen very quickly because it only has to have a common parent. In this case, the common parent is the region. So maybe you'll have like a 3-minute expectation for one of these close coordinate references. And then as we keep progressing more, and we're looking at this one, we finally get the reference in Cypress 2 back to Paxos 2, and that's sort of the hash-linked reference chain. So now this is finalizable in Cypress 2, but you can see that took more blocks because we need a higher reference, prime, So that will take a bit longer. So again, in that 9x9 or the 3x3 topology with 9 shards, that'd roughly be, an hour rather than 3 or 4 minutes. And then this is just talking about trim blocks. So then when we send blocks, we basically can propagate them. And as we're propagating them through the hierarchy, we're trimming them successively. So we're only transmitting the data that we need to the destination. And then in terms of timing of propagation, this gets maybe a little bit further than we need to go. But you can see kind of like how, as it progresses, you're successively trimming the block more and more and more. So again, you're only sort of sending what you need to where it needs to go. And one of the cool metas here is because we have this sort of symmetry between the hierarchy of chains and the state roots. The question is Quai one blockchain or many blockchains? Because they're technically all making like a commitment to the same state root. I always thought they were many blockchains for a while, and then I eventually thought they were one blockchain. Really, what you're really doing is you just have sort of like permissioned threaded execution of different parts of the state tree. It's like another way to think about this. And then the last one, this one's pretty easy, is subnets. So why do we care about subnets? We care about subnets because they help us minimize the network delay, which allows us to increase our hash efficiency and increase security. So basically, the more delay we have, the less coordinated we are, even within the context of having instantaneous consensus. We're still inconsistent. So we like to sort of make our consistency happen as quickly as we can. To do that, we need to think about the network topology. So if we look at Bitcoin, we have roughly 15,000 nodes, and it takes about 10 hops to get around the network. And you can see sort of mean propagation times of a second. So if I have 10 hops, I have 1 second ping latencies. It takes me about 10 seconds to get a block broadcast around the network, not even assuming that I have sort of any bandwidth constraints. So the proposal with Quai is, in our sort of hierarchy, is there a way that we can incentivize people to topologically organize into more network performance sets? And if we do that, we can think about the total sort of graph as this n by n, regular graph. If we start subdividing it, but we do it sort of in a topologically good way, we can minimize our ping latencies or deltas here. And we can also minimize the number of hops to get around the network. And this actually happens because the miners are incentivized to choose where they're mining based off two things. They're incentivized to choose the zone context that has the highest reward per input hash, but they're also incentivized to choose the set of peers which will propagate their block the fastest. Because if it takes me a second for my block to propagate within my set, on a 10-second block, I have a 10% uncle rate, so to speak. But if I can choose a set where they can propagate that in 100 milliseconds, I have a 1% uncle rate. So I've increased my revenue of expectation by 9%. So just having that incentive is sufficient in a competitive market to get miners to operate at the centroids of subnets, and for subnets to topologically organize into sets, which is pretty cool. Yeah, so this is just talking about those expectation values, and minimizing delta maximizes reward. So a practical example of what subnets can achieve is if in Bitcoin we have 10 hops. I guess I said 100 milliseconds here, should have been a second. Well, you get the point. We can improve the total propagation by about 10x by creating subnets. Cool. I think that's where I'll leave it. Yeah, unless... No, okay. So anybody want one more fun little meta here? Sure. So we have an interesting idea. And this interesting idea is that money basically suffers from what we like to think of as Gresham's paradox. And Gresham's law says that if there is both a superior form of money and an inferior form of money in circulation, the inferior form of money will drive out the circulation of the superior form of money. So if I have gold and I have notes, and I think the notes are fractionally reserved and like they're going down in value, I'll spend my notes and hoard my gold. Like that's Gresham's law. Now, Gresham's paradox, I would say, is that we need a monetary system, particularly in a work-based setup, wherein I can create a sustainable economic model for that work-based setup. So the chain needs to generate revenues to pay for its security over time. So I can either do that with a subsidy, or I can do that with the revenue. My revenue is transaction fees, right? My subsidy is inflationary rewards. Now, to make chains attractive for people to adopt, we'd like to have a deflationary token that's a store of value with some sort of expectation of holding value or going up in value over time. But if that exists in the context of some enterprising individual creating fractionally reserved notes, we'll end up holding all of our thing over here and spending all of our thing over here. Ergo, we won't have transactions in the network, so we won't have a sustainable model, right? So people think about this in Bitcoin, where they're already talking about is 21 million, really 21 million, because the economics of mining are getting sort of worse and worse and worse over time. So with just a 5 TPS worth of transaction fees, can Bitcoin survive? But my question with the Gresham paradox is, if Bitcoin exists and the dollar exists, can Bitcoin survive? Because if Bitcoin has better economics than the dollar, no one's going to spend it. If no one's going to spend it, regardless of the 5 TPS limit, like, how do I generate enough revenue to offset the reduction in my block subsidy? Right? So it's almost like if you only create a sound money system with one store value token, that store value token will eventually not circulate. And if your model of sustainability is transaction fees, like you've created an unsustainable model. So the idea here is we need 2 tokens then. We need one token that's a store of value and one that's sort of used as a transaction token. So we introduced 2 tokens. One is Quai, one is Q. Quai is a traditional inflationary token. We use an account model. It uses smart contracts, so there's not really privacy in that land. And you might think of it as the sort of the superior form of money because of the economics. It's expected to, its supply relative to demand is expected to go down with time. And then we have the secondary token, which is really cool here, which is Q. And what we're doing with Q is we're basically setting up a game with the miners that gives them the option of electing to take Q as a reward or Quai as a reward. But what it basically does is it creates an options game that makes Q want to approach the value of production. And the value of production, in this case, is a hash. So Q will be emitted proportional to the total hashes put into a block by a miner. And their cost of producing those hashes in a work-based system is largely dictated by global average energy prices. So the expectation here would then be if miners play that game out, the relative volatility of Q should track or be sticky to the relative volatility of global average energy prices on a 1 to 3 year term. So the cool part is I've created a transaction token, but I potentially created a transaction token that can immediately be used as a denominating quantity in transactions. And if there are any sort of oscillations in the supply chain, because most value in the supply chain is driven by energy costs, Q is technically repricing them perfectly with the change in input price of oscillation. So, you know, if my sort of energy price goes up, that'll make my aluminum price go up, which will make my can price go up, which will make my iced tea for, you know, my Arizona iced tea price go up. But that's like over this very lagged period of time. But if I just said 1 Q is 1 Arizona iced tea, and the Q sort of rises because the input cost of coal went up and causing the energy to go up, technically I'm paying more for that iced tea instantaneously, and I don't have to have this inflation effect propagate through the supply chain. So it's almost a better form of pricing, assuming that most economic profit is derived from energy input into goods. So.
You talked a bit about how now that you have this like system, your entropy measure allows you to choose like the optimal hash function. Did you say what the optimal is?
No, so we didn't. The issue with optimality is technically the optimal hash function doesn't exist yet, because if we were to design it, we would probably say that it is on a smaller field size. So our estimate would be you'd want a 96 or 128-bit hash rather than a 256-bit hash to sort of get maximal finalization. In terms of sort of like the compromises, right? Hash functions are kind of black magic, right? In cryptography, they technically like don't exist mathematically. So, as a project with, our resources, we don't have the hubris to think that we should try to develop a new hash function, especially in a different field size. So we're we're picking from what exists. And then, this is sort of that theoretic optimality. It doesn't take into account sort of like economic concepts. So from our perspective too, we think that there is some weight to sort of decentralization arguments. And I think there's also arguments around sort of global strategic censorship arguments. Specifically, if you have a GPU-friendly algorithm, your ability to get people to coordinate is their ability to get GPUs. But if I have an ASIC, like that sentence turns into their ability to get ASICs. Now, if I have an application-specific device, that's very easy to control at national borders. If I have a GPU, like, what are you going to do, not have GPUs in your country? Right? So because it's non-application specific, if you have a situation where nation states start to care about who has the mining hardware, GPUs are much more resilient to that than ASICs.
So then can you say a bit how that plays into the economic analysis of Q? Because if you choose a hash function that does have these geographical implications, then the price of Q isn't necessarily dependent just on energy prices.
It's also dependent on the big input here you're referring to is the efficiency of FET-based GPUs. So with Q, right, the goal is to keep it stable over sort of a reasonable time frame for money. Now, hash rate for FETs, right, it sort of doubles, I think, like every 20 months or so. But the curve and sort of the plateau in the curve at this point is pretty predictable. So we can sort of a priori put that into the function as a discount value and sort of help that stability extend its time window. We don't need to get it perfect, but we think we can get it kind of so, you're going to be sitting at every year, you're kind of like plus or minus 10%. If you have a way to measure that efficiency, which we haven't come up with, that would be awesome. But right now, we think, historic data and just an efficiency curve is the way to take that biggest sort of component out of Q. Great question, by the way. Yeah. So when we talk about the implications, what has this actually done for us? In our 9-shard topology, we've run a network. This network has 2,000 nodes around the globe. And when we've done our TPS tests, you can see that we can do 2,000 TPS sustainably, which is matching like Visa's average throughput in a fully decentralized global proof of work network. So one of the cool things is that's only a 9-shard topology. We can obviously have more shards, and we haven't really pushed on the optimization of throughput in any single shard to any degree. So pretty cool stuff.